The internal combustion engine remains a pivotal component of modern transportation, powering a vast majority of vehicles on our roads. Its design represents a complex interplay of thermodynamics, mechanics, and material science, all working in harmony to convert fuel into motion. Understanding the fundamentals of engine design is crucial for anyone involved in the automotive industry, from engineers to technicians. This essay will delve into the core principles of engine design, exploring the various components and systems that contribute to its overall performance. Engine design is a continuous process of refinement, driven by the need for improved fuel efficiency, reduced emissions, and enhanced performance. The demands placed on modern engines are constantly evolving, pushing engineers to develop innovative solutions. From the materials used to the intricate control systems, every aspect of engine design plays a crucial role in achieving these objectives. The quest for optimal engine performance is a testament to human ingenuity and our relentless pursuit of technological advancement. This exploration will cover key parameters that define engine performance, including compression ratio, pressure-volume diagrams, and engine capacity. We will also examine the design considerations for critical engine components, such as the crankshaft, cylinder head, and valve train. Furthermore, we will delve into the intricate systems that support the combustion process, including cooling, lubrication, intake, exhaust, and fuel injection. Finally, we will discuss the optimization strategies employed to enhance engine efficiency, touching upon thermal, mechanical, and volumetric aspects. By understanding these fundamental principles, we can gain a deeper appreciation for the complexity and sophistication of modern engine design. This journey into the heart of the machine will illuminate the intricate workings of this remarkable invention and its enduring impact on our world. Several key parameters define the performance characteristics of an internal combustion engine. Compression ratio, the ratio of the maximum to minimum volume in a cylinder, plays a crucial role in determining the engine's efficiency and power output. A higher compression ratio generally leads to better fuel economy and increased power, but also requires higher octane fuel to prevent knocking. Understanding this balance is essential for optimizing engine performance. Pressure-volume diagrams provide a visual representation of the thermodynamic cycle within the engine cylinder. These diagrams illustrate the changes in pressure and volume during the intake, compression, combustion, and exhaust strokes. Analyzing these diagrams allows engineers to gain insights into the engine's performance and identify areas for improvement. The shape of the pressure-volume diagram can reveal much about the combustion process and its efficiency. Engine capacity, often expressed in liters or cubic centimeters, represents the total volume swept by all the pistons within the engine. This parameter directly influences the engine's power output, with larger capacity engines generally producing more power. However, larger engines also tend to consume more fuel. Balancing power and fuel economy is a constant challenge in engine design. Another crucial parameter is the engine speed, typically measured in revolutions per minute. The engine's power output varies with speed, reaching a peak at a specific RPM range. Understanding the relationship between engine speed and power is essential for optimizing performance and fuel efficiency in different driving conditions. The design of the engine's components must take into account the desired operating speed range. The crankshaft, a critical component of the engine, converts the reciprocating motion of the pistons into rotational motion. Its design must withstand immense forces and stresses while ensuring smooth operation and minimal vibration. The crankshaft's material, shape, and construction are carefully engineered to achieve the desired balance of strength, durability, and performance. Balancing the crankshaft is essential for minimizing vibrations and ensuring smooth engine operation. The crankshaft is connected to the pistons via connecting rods, which transmit the force of combustion to the crankshaft. The design of these connecting rods is equally crucial, requiring strong, lightweight materials that can withstand the high pressures and temperatures of the combustion process. The length and shape of the connecting rods influence the engine's stroke and overall performance characteristics. The crankshaft's rotational motion is transmitted to the vehicle's wheels through the transmission and drivetrain. The crankshaft's speed and torque are carefully managed by the engine control unit to optimize performance and fuel efficiency. The ECU monitors various engine parameters and adjusts the fuel injection and ignition timing to ensure optimal combustion. The design of the crankshaft must also consider the engine's firing order, which determines the sequence in which the cylinders ignite. The firing order is carefully chosen to minimize vibrations and ensure smooth engine operation. The crankshaft's counterweights help to balance the forces generated during combustion and reduce vibrations. Section 4. Cylinder head and block, containing the combustion. The cylinder head and block form the core structure of the engine, housing the combustion chambers and supporting the various engine components. These components must withstand the high pressures and temperatures generated during combustion, while maintaining structural integrity. The material selection and design of the cylinder head and block are crucial for ensuring engine durability and performance. The cylinder head houses the intake and exhaust valves, spark plugs in gasoline engines and fuel injectors. Its design must optimize the flow of air and fuel into the combustion chamber and the expulsion of exhaust gases. The shape and size of the combustion chamber significantly influence the engine's efficiency and power output. The cylinder block houses the cylinders and the crankshaft. Its design must provide adequate support for these components while maintaining a rigid structure. The material selection for the cylinder block is crucial for ensuring durability and resistance to wear and tear. The cooling passages within the block help to dissipate heat generated during combustion. The cylinder head and block are typically made of cast iron or aluminum alloys. Cast iron offers excellent durability and wear resistance, while aluminum alloys provide lighter weight and better heat dissipation. The choice of material depends on the specific application and performance requirements of the engine. The design of the cooling passages within the block is crucial for maintaining optimal operating temperatures. Section 5. Valve train dynamics, controlling the flow. The valve train is responsible for controlling the flow of air and fuel into the combustion chamber and the expulsion of exhaust gases. It consists of the camshaft, valves, springs, rockers, and push rods in some engines. The precise timing of the valve opening and closing is critical for optimizing engine performance and efficiency. The camshaft, driven by the crankshaft, controls the opening and closing of the intake and exhaust valves. The camshaft's profile determines the valve lift and duration, which significantly influence the engine's breathing and power output. The design of the camshaft is carefully optimized to match the engine's operating characteristics. The intake valves allow fresh air or air-fuel mixture to enter the combustion chamber, while the exhaust valves expel the burnt gases. The valves must open and close rapidly and precisely to ensure efficient engine operation. The valve springs play a crucial role in closing the valves quickly and preventing valve float at high engine speed. Valve timing. The precise timing of the valve opening and closing relative to the piston's position is crucial for optimizing engine performance. Variable valve timing, or VVT, systems allow for adjustments to the valve timing based on engine speed and load, further enhancing performance and efficiency. VVT systems can improve fuel economy and reduce emissions. Section 6. Engine systems supporting the combustion process. Several supporting systems are essential for the proper functioning of an internal combustion engine. The cooling system, typically using water or coolant, regulates the engine's temperature, preventing overheating and maintaining optimal operating conditions. The cooling system includes a radiator, water pump, thermostat, and hoses. The lubrication system circulates oil throughout the engine, reducing friction between moving parts and preventing wear and tear. The oil also helps to cool the engine and remove contaminants. The lubrication system consists of an oil pump, oil filter, and oil passages within the engine block. The intake system delivers air to the engine, while the exhaust system expels the burnt gases. The design of these systems influences the engine's breathing and volumetric efficiency. The intake system may include an air filter, intake manifold, and throttle body. The exhaust system consists of an exhaust manifold, catalytic converter, and muffler. The fuel injection system delivers fuel to the combustion chamber, either directly into the cylinder, known as direct injection, or into the intake manifold, known as port injection. The fuel injection system is precisely controlled by the ECU to ensure optimal air-fuel ratio and combustion efficiency. The fuel injectors are electronically controlled to deliver precise amounts of fuel. Section 7. Thermal efficiency, maximizing energy conversion. Thermal efficiency represents the percentage of the fuel's energy that is converted into useful work. Maximizing thermal efficiency is a primary goal in engine design, as it directly translates to better fuel economy. Various strategies are employed to improve thermal efficiency, including optimizing the combustion process, reducing heat losses, and improving the thermodynamic cycle.